Alright, welcome to another AQA A-Level Chemistry video. Today I'm going to make a video on hydrogen 1 NMR. Try and stick around this video. I don't know how long I'm going to make this video. But I will always try to make my videos as short as possible. However, I want to make them educational. I want to make sure that you gain something from this. I don't want to just, me saying notes, try and give you everything that you need. So, you know the usual. If you've been watching this channel for a long time, or from majority of videos I have, I do try to make it as short as possible. However, if I feel like they need to say something, sometimes I do just waffle, to be honest. Maybe I am just waffling right now, but yeah, I don't want to talk a load of horse shit and then you miss out on the point I'm trying to say. But today is going to be quite a complex video, and I will try to split this video into two. So this will be a two-part video. This is going to be part one, and yeah, I'm trying to give you as much information as possible as I go through it, so that you gain clearly all the information that you need for NMR, so you have a good understanding of what's actually going on. And it's relevant, and it is all relevant, because if they ever ask you a question related to why you get a result for NMR, or if they try to give you a result and explain, if they can, AQA. I'll be honest with you, right? AQA like to just take the absolute mick. They do. I say they take the piss. Really do. They actually just take the piss. So they could, give you a reading and say what results are you expected to get, or they can give you a result and they may ask you to explain. So you gotta have a good understanding. I mean, it's good to have a good understanding anyway, but you always try to throw you off a little bit. So I'm gonna try and give you as much information as I can, and then explain why it has that result, so that you can do vice versa either way. If you need to explain and give a result, or if they give you a result and you need to explain. But yeah, so I'll go through that. So hydrogen 1 NMR is the next type of NMR we'll study. It's slightly harder than carbon-13 NMR, which I'll leave a link in the description, which is the previous video. But the basic principles are generally the same. Now, I want to clear something up, right? So I'm going to go back to this video here, Understanding Nuclear. Yeah. So I didn't make a slight error, but I didn't go into as much depth as I wanted to with hydrogen, when I went for this video for Understanding Nuclear Magnetic Resonance, or Understanding NMR. Now, oh yeah, I forget you guys can't see my hand gestures, but it doesn't matter anyway. It doesn't matter at all. So I made it very clear, right, that in hydrogen 1 NMR, you need to have an overall spin. Now, the overall spin is because so you need to have an odd nuclear number to have an overall spin. Why is that? Because when you have an even nuclear number, there's no overall spin. So what I mean is that if you had, like, for example, if I had, carrying spaces here? Yeah. Okay, let's say I have this little box here, right? I had some nuclei going in different directions. So if it's an even nucleon number, there'll be no overall spin. They're equally going in this way, that way, this way, that way. There's no overall spin. However, when it's odd, there will be an overall spin. So say and that overall spin is needed. That's so cool. That's what we measure. We're measuring that overall spin. Now, kind of take it down here, right? We're able to measure the overall spin, but there's still some, even though there's an overall spin, there's still some going, is still two. In this example, obviously it's going to be much more in the real thing, but if we're going here, there's 3 going in this direction here. It's 3 going in this direction, and there's 2 going in this direction. There's still 2 going in the opposite direction. And that's what allows us to determine our energy difference, or our energy gap, right? So here's the example that I had before, right? Let's say it's just these two. Say the overall spin is going in this direction, like with the blue arrow here, right? We said that if it's going with the overall spin, they're low energy nuclei. Whereas if it's going against the overall spin, they must have sufficient energy to go against the overall spin, and they are high energy nuclei. And that's what I'm going to go bring down here, right? And this is actually how we measure. I wasn't very clear on how we actually measure, how I'm actually able to measure the energy gap in NMR. How basically I wasn't clear on how we actually get to here. That's actually terrible. I apologize because I wasn't able to actually give you a good example of why we actually. I said, why did that happen? Anyway, well, why we actually get to here from here, right? And the reason is, so what we're actually doing here, right? So as I said before, as I said initially, there are the majority of let's say this is the nuclei spin, right? I'm going to draw here. This is the nuclei spin here. The majority of the nuclei, so let's put 5 down here, are spinning in the same direction as the overall externally applied magnetic field, right? When there's an odd nuclear number, there's an overall there's a magnetic field. When there's an odd nuclear number, there's a magnetic field. When there's an even nuclear number, there's no magnetic field because there's no overall spin. So when you have an odd nuclear number, there's an overall spin. Yes. Yeah. So let's say there's the overall spin here. An overall spin, nuclei that are going with the overall spin are lower energy nuclei. They have if it's going with the direction, here we're saying that the green arrow here represents the overall spin. So any nuclei that's going in the same direction as the overall spin is no lower energy nuclei. Now I've made that very clear. I've said it like 3 times now, so you get that point. So that means that any that are opposing, let's say we put like 3 here. We could do 4, but let's just put 3 for the sake of it. I don't want to make too much space, but you get the point, right? Actually, you know what? Let's put 4. There you go. There you go. Right? So now we have a nuclei with. So any actually no, I don't like having 4 there. I want to make it very clear that there's more on the top than the bottom here, right? So if it's going downwards here in this direction, it could be any direction, but just to show you that this is the opposite direction, nuclei that are spinning in the opposite direction are higher energy nuclei to go against that overall spin, to go against the force of the. Remember, this is a force, right? To go against that force of the overall spin, they must have high energy. And that's what establishes the energy gap. The energy gap is the difference between the nuclei being able to spin in with the overall spin and against the overall spin. So to actually change it to go from a lower energy level, to change it from going from one direction to the other, there's a certain energy gap, right? What we're doing is that we are applying, what NMR machines do is that they release radio waves, and those radio waves, as I said here, I'll be show here. Oh my gosh, that's terrible there. This radio wave here. Use that again. This radio wave here is what we're doing. So we are trying to create these. Can't speak right now. We're trying to cause that these nuclei here to reach the energy gap. We're exciting these nuclei to reach the energy gap here, to breach it. So we're giving it enough energy to reach the energy gap. But once it gets to here, change color. Once it gets to here, it's unstable to have all of them under that energy gap. And what they'll do is that they will de-excite now. So once they get to here, they will de-excite to, because they're unstable when you get to here right now. You can't have that many nuclei with a high energy level like that. So they will de-excite back down, change color. They'll de-excite back down to this lower energy level. But when they de-excite back down to lower energy level, they'll release energy. They'll release energy probably as radio waves as well. Are we measuring? We're measuring it in parts per billion. That's a chemical shift. Yes. We're measuring the energy. I don't want to go in specifically how the energy is being detected. It's probably at some sort of wave. But more importantly, once it gets de-excited back down to an energy level, it releases energy, I believe, as a wave, as a radio wave. Did I say energy wave? Yeah, if it's a signal, it must be some sort of energy, radio wave, a wave of sorts. So even if it's not specifically a radio wave, I'm pretty certain it is a radio wave. But all I'm saying is that, as I said before, step 1, right? Radio waves, we have the energy gap here. I've explained why there's an energy gap already. But now the what we've established that there's an energy gap here, right? I'm just saying it again so that because I think the last part was a bit confusing, so I'm gonna say it again, right? We already established that there's an energy gap. We apply a radio wave to allow to allow the nuclei with the lower energy to get excited to a higher energy, which is what I've shown here, right? But once they get to here, they're unstable, so they de-excite back down, right, to that lower energy level. But when they do that, as they're de-exciting back down to the energy level, obviously if they're going from a high energy state to a low energy state, so therefore energy has to be lost, and it's releasing that energy as a wave, and that's what we're able that wave gets detected by a detector in the NMR machine, and that's what we're able to detect, and that is what creates that what we're detecting is what the when we detect that wave, that's what enables us to create this graph where so energy is being lost as it de-excites, and that energy is being released as a wave, and we're able to measure that wave that's being detected. Eventually, this wave will reach a detector, right? And then we're able to read that signal from the detector, and we create this graph, or the machine will. It's usually a computer, right? The computer will then generate this graph based off the wave that it's received at the detector. Now, hopefully that made sense. Hopefully it made sense. If it didn't make any sense, leave a comment in the description. Leave a comment in the comment section, and I'll try and explain it again. But hopefully that made sense. That's how we're able to create this. This is just the energy that's been released from the nuclei being de-excited back to its lower energy state. Right. Hopefully that made sense. Now I'm gonna go back down to here. Now I said that's our basic understanding. As I said before, that is our basic understanding of NMR, right? So that's basic understanding of how we're able to get the graph, or not the graph, the spectra. There we go. That's the correct word. That's how we're able to get the spectra. But we know that's how it happens. But we also know that different that was carbon-13 or carbon, or but it can apply to carbon-13 or hydrogen-1 NMR. That is how we measure it, right? Now, we also know that I'm going to talk about hydrogen-1 here, but the same can be applied, as I said before, the same applies to carbon-13 NMR as well. But I'm talking about hydrogen-1 here, so I'll talk about hydrogen-1. So as I already explained how we create the spectra in general, but we know that different hydrogens in different environments, or not different hydrogens, but different hydrogen environments, or different environments that the hydrogen is in, is what creates different peaks, or different different peaks obviously, but the position of the peak is at different values on the x-axis, or different chemical shifts. The chemical shift is determined by the environment that hydrogen is in, right? So what I mean by that is the hydrogen next to a, so this is the hydrogen that we're talking about here, right? This is one hydrogen environment. I already explained what hydrogen environments are anyway in my previous video, I believe, so I'll leave a link to the last two videos anyway. But this is the hydrogen environment is the environment that carbon is in. It's very straight to the point, right? It's just what that hydrogen is surrounded by. Think about environment. Your environment is, if you're in a park, that's one environment. If you're in a building, that's another environment, right? So this hydrogen is next to another, is bonded to a carbon that's bonded to another hydrogen. This hydrogen is bonded to a carbon that's in a carbonyl bond. That's two different environments. Now, what actually happens when we're determining the environment? What's actually causes a difference in so obviously we know, have I got an example of a spectra here? Hopefully I've got an example of a spectra, right? So what's causing, why is this spectra, well, actually I'll use that one. Why is this here in a different position to here? Why is that? There's a reason for that they're in different see, why is that there? Why is that there? Why is that there? Why are they at different positions? We know it's at different environments, but why does the environment, basically we already know, I've already told you that the environment is what determines the chemical shift, but why? And there's a reason why that actually happens. Don't know, sorry about that, I don't know why that happened there. I always forget to do that. Anyway, there's a reason why the environment affects the chemical shift, and I'll explain why. And it's all to do with about shielding. I mean, electron shielding. I know NMR is about nuclei, but the electrons affect how the nuclei behave. Now, what I mean by that is that we've already established that nuclei have an overall spin, and but the electrons also affect how well they spin. So when you have, I'm not really an expert fully on this, so I'm not going to go in too much detail. But from what I understand, is that electrons do have an impact on shielding. So electrons have an impact on basically the shielding. How the electrons affect the shielding, affect the nuclei. And what I mean by that is that the less shielded the the nuclei is on the hydrogen, the larger the value, or the higher the chemical shift. Why? It's because what affects the chemical shift is the energy gap. So the larger the energy gap, so here we've got one energy gap here, and this is another energy gap. The larger the energy gap, the higher the energy released when it de-excites back down again. So the more, and if there's the more energy getting released after it de-excites, the signal detected, or the energy detected at the detector, will be higher, and hence the chemical shift will be higher, right? So here, the carbon-hydrogen bond here, we can clearly see here that the bond is in the middle. Now, electronegativity does have an effect on shielding, right? So carbon-hydrogen bond, this is a very non-polar bond, because hydrogen is not that polar, carbon's not, not polar, so the bond is in the middle. And therefore, because this is a non-polar, this is a non-polar bond, the electrons are exactly in the middle, therefore there's more shielding. The electrons are closer to the hydrogen, and there'll be a greater effect of shielding, right? There's a greater effect of shielding that's going on here, right? Or generally between these two here, but it does affect this in a way as well, right? If there's more shielding here, then the energy gap will be less. The overall spin, there's not a great difference. The energy to get to the other, the energy required to change the overall spin of the nuclei is less. Because it's less positively charged, less energy is required. Because of the nuclei's ability to cause shielding affects the overall spin. So the more shielding you have, the easier it really is to change the overall spin. And if it's more easier to change the overall spin, because there's I assume something to do with the fact that the electrons are negative, they repel it. And remember, this is all about force, right? If it's repelling it, it's probably changing the way the effect of the magnetic force. It's probably changing the way that it's spinning, or it makes it easier for it to spin in one direction than the other. Whereas if there's less shielding, that positive charge, that spinning direction, it's not really to do with charges here, but it's more to do with the force. That repulsion effect is less, and therefore that spinning force is much greater, and therefore more energy is required to change the overall spin. And that's all that's happening here. So carbon hydrogen is not a very polar bond. So carbon hydrogen is not a very polar bond. So the electrons are in the middle, so there's more shielding, and therefore the energy gap is much less, and hence the overall spin. So the energy gap is less, and therefore when the electrons get excited, or when we add what's it called again? The radio waves, they excite the nuclei here. They get excited to a high energy level, then this unstable here gets de-excited, and then energy released, and the energy gets released as the nuclei gets de-excited after being excited, of course. and that energy release is in the form of a wave. Remember, waves in general are energy carriers, so they carry energy. That wave will then reach a detector and the detector is recording a wave at a certain frequency, and that's what's determining our chemical shift, right? Whereas here, this is a hydrogen that's bonded to a carbon that's on a carbon bond. Now, oxygen is very, very electronegative, and it's pulling the it's pulling it's the as you can see here, we usually expect when we're having, for example, a carbon hydrogen bond, the electrons to be in the middle of the bond. But because the oxygen is so electronegative, remember, electronegativity is the ability of an atom to attract a lone pair of electrons or attract a valence pair of electrons in a covalent bond. Now it's so electronegative, it's pulling electrons towards the oxygen, more towards the carbon, and therefore there's less shielding here, there's less shielding here, less shielding here. I'm not worried about the carbon, I'm worried about the nuclei on the hydrogen, right? So because of that now, because these electrons are further away, there's less shielding, and we'd expect, as I said before, I already explained the reasons how it affected, but our energy gap would be much higher. If our energy gap is higher, means that when they more energy is required from the radio waves to excite nuclei to that higher energy level. But it also means that when they get de-excited now, they de-excite with more energy as well, and therefore they would release a higher frequency, usually be a higher frequency wave, I believe, towards the detector that detects it, and they will detect the high frequency, and our chemical shift will be much higher. So you'll notice that with these more polar bonds, or more polar compounds, or electronegative groups, right? The chemical shift that's detected on the hydrogen that's bonded to that carbon. Again, if this is carbon-13 NMR, then we're talking about the carbon here, but we're talking about hydrogen one here, so that's why I say it like that though. But we'll notice that the chemical shift when it comes to more polar compounds is much higher, and it's for that reason. And yeah, that's it really. I just wanted to clear that up before, so that people can kind of understand. The reason I tell you this, you probably think, David, why the hell you told me all of this? Like, it's not really relevant to me. It doesn't seem relevant to me. I thought all we need to know is the spectra, how to read the spectra, and all that. But it's not like IR. Now, if IR, you just need to know the spectra, and that's it, and then everything's fine. And usually for IR, that's really it, really, to be honest. But with NMR, sometimes they like to ask 1 or 2 mark. I know I'm maybe dragging it for 1 or 2 mark questions, but I feel like every mark counts really, so you're better off just knowing it. But yeah, they may ask questions such as there's a reason why I'm saying what I'm saying. I'm not just waffling for no reason. They may ask a question and say, where would you expect the peak to be for this compound, right? And they've drawn your compound, it has an electronegative group, and you'll be able to explain and say, you don't have to go into great detail. Again, this is probably like a 3 mark question, but you're able to say, because it's got a polar group here, there's less shielding, and therefore I'm not going to go into great detail because I've already explained in great detail already why, but less shielding, therefore the energy gap would be higher, and then more energy is dissipated when a nuclei returns back to a lower energy level, and then when that happens, you get a higher that more energy goes to the detector, or I say more energy. That higher energy that gets released goes to the detector, and you get a higher chemical shift. Now, you may not get a question like that, but I've seen questions where they ask about questions where they expect you to kind of have an understanding of where and which part of the chemical shift you'd expect to find a compound if, or what type of bonds may cause. So I'm kind of talking way too much here right now, but they may ask you a question, like a small follow-up question of where you'd expect the peak to be based on the type of compound or what you know about it. Or vice versa, they may give you the peak and they may ask you, why is the peak for this much higher than a carbon hydrogen bond, for example. And that's what you have to explain here. What I've just said. Yeah, that's that. I just wanted to cover that one up. But I'll quickly go through this. How much of this do I have to go through here? Great. Okay, cool. No problem. Now, sorry, I have to go, just kind of have to go through this one quickly here. But chemical shift, right? Sorry about this. There we go. All right. So, chemical shift. Now I'm finally gonna go actually onto the part of the video now that's relevant now for you, because you probably listened to that part last part. That's kind of me adjusting from the last part. But I'm gonna actually start talking about the video right now. Chemical shift. So, as in carbon 13 NMR, hydrogen 1 NMR spectra display signals at different chemical shift values, and these chemical shift values represent different hydrogen 1 environments. So, for example, if the spectra has 4 peaks, there are 4 different chemical environments, with an unknown number of hydrogen 1s in each environment, which is pretty self-explanatory. The amount of environments the number of peaks you have, is basically the same number of environments you have. It's not the same number of hydrogens you have in your compound, but it's the same number of hydrogen environments you have. So, for example, methane has 4 hydrogens on it, but they're all in the same environment, so it'll be all one peak. Really, if you get what I'm trying to say here, the integration, like I said, the integration ratio of it, the integration of it, would be resulting in how many hydrogens you have bonded to that carbon, really, or next to it. Obviously, I'll go and explain what N+1 rule is, but yeah, the number of peaks you have is just representing the number of hydrogen 1 environments that you have. So we can use chemical shift tables. Have I gone through that part here? Yeah, we can use chemical shift tables to identify hydrogen 1 environments and function groups from the signals in spectra. Now, I've already explained what you already have. This is the sheet that you have in your exam, the data sheet that you have, and this, the last one was carbon 13. This is hydrogen 1 NMR. So this is what, if you're looking for hydrogen 1 NMR, this is what you'd be looking at. If you're doing carbon 13 NMR, then that's there, obviously. But today we're focusing mostly on hydrogen 1 NMR. Now, tetramethylsilane. So, as in carbon 13 NMR, hydrogen 1 NMR's reference is tetramethylsilane, sorry, or TMS. And you also need to choose the solvent you use for NMR very carefully. There are examples like CD4, right? So I made a mistake. Again, I'm making plenty of mistakes, but in my last video, that's what I said, NMR is kind of a difficult topic, so make sure you get it done right. But it can be very easy. You can make it very easy. As long as you get to the exam, you know what's going on. By the time you get to exam, you should know what's going on. It's difficult at the start only. But anyways, in the last video, I said that CD4 was like a type of reference. It's not a reference. It's a type of solvent that you would use to dissolve your compound in. And there's a reason why you need to pick your solvent very carefully. And I'll go through that I have in the part 2 of this video. This is a 2-part video. In a 2-part video, I explain very carefully why you need to pick your solvent very carefully. All right, so, but one of the examples is CD4. As I said before, when I'm talking about the reference, TMS is a chemical shift of 0 ppm. I did go over what it was. So the tetramethylsilane is non-chemical, is not toxic, so you don't need to do it in a fume cupboard. It is, obviously, it has all the carbons are in the exact same environment. I believe cost is another one. But I know it's those two at least. But I said before, looking at it, when I go through exam papers, you'll get a question on it and you'll be able to see what it is. But those are the two. In fact, you know what? For the next part of the video, this is a 2-part video. So when I do the second part of this video, then you'll be able to see. I'll go back and look at the 3 reasons, because there's usually 3 reasons. I think they only ask for 2, but it's good to know all 3 of them anyway. But I will go through all the 3 reasons why tetramethylsilane is a good reference. But yeah, TMS is a shift of 0 ppm. TMS produces a single peak because the hydrogen 1s in TMS are in the same environment. So that's why you see when you're looking at NMR, there'll be one single peak. Yeah. There should be a peak here. I don't know why it's not a peak here, but there should be one single peak at 0 ppm, or unless they don't choose to use it, because everyone knows there's a peak at 0 ppm anyway, but there should be one there anyway. All right, so and that's what tetramethylsilane looks like. It's just a tetra. It is literally what it says, a tetramethylsilane. All these hydrogens are in the exact same group. Again, I've already said this in my previous video when I was doing carbon 13 NMR. All hydrogens are in the exact same environment. Anyway, Signal ratios. So an extra piece of information that hydrogen 1 NMR gives us over carbon 13 NMR, which is why I said it's better than using carbon 13 NMR, gives us a little bit more information. It's based around the ratio of the areas underneath the signals. So the ratio of the areas reflects the ratio of how many protons are in the same environment. For example, if there are two singlet peaks and one peak is twice as big as the other, this means that the chemical environment of the bigger peak has twice as many hydrogen ones as the other environment. So, what this means here is that how can I? Right. So this what this peak here is telling me that this is a singlet peak. Have I gone through? I haven't even gone through the splitting patterns yet. But all it's telling me that they're two different environments. We know clearly here that the chemical shifts here are different. This is very different from this. This is a different environment to this environment because they're not exactly in the same line. If they were in the exact same environment, you would be able to tell the difference because they'd be in exactly the same line. The same way at when you're looking at an analog clock, and it's midnight, and it's midnight is usually like that. If I had a clock, right, it'd be straight up. You can't tell the difference between the hour and the minute hands because they're exactly in the same line. Now imagine that was hydrogen, right? If hydrogen are in the exact same environment, these two here will be in the exact same position, right? They'll be in the exact same position. You wouldn't be able to tell the difference, but that's not the case here. These are clearly two different environments, but in the two environments, what this tells, because there's a difference in the area underneath the graphs, i.e., it's very difficult to see it, but the computer that you use will do an integration ratio. There's twice as many hydrogens in this environment than there are in this environment. And I'll tell you, and when I do exam questions, doing exam questions. That's what I said. Doing exam questions is the best way to revise because you're able to understand much better than looking at notes. That's the best way to revise, doing exam papers and doing them early. But when you're doing exam papers, this is much easier to explain why this is so useful, because it tells you how many hydrogens are. It tells you it's a singlet peak, yes. So there's only well, when I go to singlet splitting patterns, you'll see, but it tells you how many hydrogens are next to it. But it doesn't tell you how many hydrogens. That wouldn't tell you how many hydrogens are on that carbon. This tells you realistically tells you how many hydrogens are on that carbon, because that's what the integration ratios are good at telling you at. And especially as a ratio 2 to 1, it's double the amount of hydrogens in this environment compared to this environment. All right, splitting pattern. So this is what splits. This is what difference between carbon 13 NMR and hydrogen 1 NMR. So H1 NMR gets slightly harder than carbon 13 NMR when we consider splitting patterns, but this pays off because it gives us a lot of useful information. For example, signal splitting. So in hydrogen 1 NMR, the main signals that represent different chemical environments have fine splitting patterns. Now, what I mean by fine splitting patterns is this here, right? This would be a triplet. This isn't again, AQA love doing this. They don't like making it clear, but this is a doublet and this is a singlet here, but they represent a specific thing. They represent it's actually very useful. As I said, H1 NMR splitting makes it a bit more difficult, but it gives us a lot more information. So it being difficult, it is difficult, but there's a payoff to it. It gives us more information, right? So main signals may be split into numbers of fine peaks. Peaks are different names depending on how many splits they have. For example, if there's no splitting, which is a singlet, that means that there's so no splitting is a singlet. Split into 2, which is a doublet. Split into 3, that's a triplet. Split into 4 if there's 4 peaks like this, 2, 3, 4. It wouldn't be a loop. It shouldn't be a loop there. 1, 2, 3, 4. That's a terrible drawing, but hopefully you get what I'm trying to say here. That would be a quartet. And anything on AQA spec, anything split into 5 or more is called a multiplet. However, for reference, you can clearly see that what the pattern is: singlet, doublet, triplet, quartet, quintet, sextet, etc. But 5 or more is just considered to be a multiplet. If you did accidentally say quintet and sextet, they probably would give it to you. I've seen it in marketing; they usually give that as well. But yeah, makes your life a bit easier. But information, what does the splitting actually tell us? Why is that useful? The reason is that the information from splitting is that signal splitting helps us to work out the number of hydrogen ones in different environments. But where this is not as straightforward, the number of fine splittings is equal to the number of hydrogen ones on the adjacent carbon plus 1, right? So this is called the n+1 rule. What does that actually mean? So diethyl. So I'm gonna show you the NMR, the H1 NMR of diethyl ester, right? Diethyl ether. So there are two different protein environments in diethyl ether. This is one environment. Oh, sorry, wrong one here. There's only two environments here. This is the same environment as this, but this is also the same environment as. I'll use different color for that one there. Those two are in the exact same environment, but this is also in a different environment here. So I'm not even going to look at that. What would I expect? I would expect to see here a triplet and a quartet. Why? We follow the n+1 rule. The n+1 rule for the number, so the number of splittings equals the number of hydrogen ones on the adjacent carbon plus 1. So for example, this hydrogen here, so this hydrogen here, right? I would expect it to have a quartet, represent a quartet. Now the signal splitting for the ratios for this would be 2-1, or I guess 6-3. Sorry, 6-4. The ratio would be 6-4. Because there's obviously there's 6 hydrogens in the same environment, and there's 4 hydrogens in another environment. So 1, 2, 3, 4, 5, 6. They're all in the same environment, and then this one here would be 1, 2, 3, 4. But don't have to worry about that. That would be that you don't have to worry about that one. So that'll be. I guess you can round it down to 3-2. But we're not talking about the integration ratios here right now. What we're talking about is the splitting. Now this hydrogen here is simple. This hydrogen here is in an environment where it's next to, right? I'll use this one here, white. So it's adjacent or next to, so this hydrogen is bonded to a carbon. I'm not doing a mechanism here. I'm just showing you the where it's bonded to. This hydrogen is bonded to a carbon that's adjacent to a hydrogen that's bonded to a carbon that has 2 hydrogens on it, right? So this hydrogen is bonded to a carbon that's adjacent to a carbon with 2 hydrogens on it. So if there's 2 hydrogens on the carbon that's adjacent to this hydrogen, if you follow the n+1 rule, 2 + 1, I'm not insulting your intelligence, but that's 3. Now what would this be? So if that we talked about this hydrogen here. Oh, that does make it clear. We've talked about this hydrogen here. What about this hydrogen? That's what now this hydrogen here is in the exact same environment as this hydrogen, and then this hydrogen, and this hydrogen, and this hydrogen, and this hydrogen. So they would overlap one another. The only way we can tell that there's 6 hydrogens here is by the integration ratios. But we'd expect so we'd only here expect to have 2 peaks here. But this clearly would have this hydrogen here, and this hydrogen, 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 and this hydrogen would all represent a triplet. It would be triplet because it'd be 2 + 1, that's 3. So it'd be I was about to say something else there. I was about to say, yeah, it doesn't matter. We're not gonna be making jokes about Michael Dapper here, but yeah, this is gonna be a triplet because we have two hydrogens next to it plus 1 triplet. You would get that point. Now, what would this represent here? I think you can already tell what's going on. What environment would this hydrogen, this hydrogen, this hydrogen? Remember, all of these ones here are in the exact same environment. What environment would they be in? I'm gonna pause the video now and try and answer that. But if you already pause the video and you already know the answer to it, it's clearly gonna be a quartet. Why? Because this hydrogen is next to. Oh, actually, would it be? Yeah, it would just be that. Yeah, it would just be that. Sorry, I forgot that these are. If this oxygen wasn't here, then if this oxygen wasn't here, then it'll be a lot different. But I forgot that there is an oxygen here, so we don't have to worry about that. But yeah, anyway, come back to this. This will be a quartet. Why? Because it's next to this hydrogen is bonded to a carbon that's next to a carbon that's bonded to 3 hydrogens. So that's 3 plus 1, 4. Hopefully that made sense. Because this hydrogen here is bonded to a carbon that's adjacent to a carbon that has 3 hydrogen bonds to that carbon, or it's next to 3 hydrogens, right? I want to say next to 3 hydrogens. It's adjacent to a carbon that has 3 hydrogens bonded to it. 3 plus 1, that's 4 hydrogens in total, and that'll be so that's 4 hydrogens. Sorry, that's 4. That's 3 plus 1 was 4. Therefore, we would expect a quartet. And lo and behold, we would have this here. Now, what's interesting is that it's our quartet. Yes. What would expect here? Why I said it. So remember what I said at the very start, right? About why this would be. I always keep changing these. Why this is here and why is this here? So I already explained the splitting pattern here, but why is this much further away? Why has this got a higher ppm value? Why has it got a higher chemical shift value than this? Because the quartet here, this quartet is being represented by this carbon here. Remember the carbon here. Sorry, not the carbon, the hydrogen. This hydrogen here would be represent the quartet because it's next to the hydrogen, next to the carbon that's bonded to 3 hydrogens on it, right? So it's this hydrogen that's representing the quartet. When I mean this hydrogen, you know what I mean. I mean this hydrogen, this hydrogen, this hydrogen, and this hydrogen. They're all in the same environment, right? So this, because it's bonded to an electronegative oxygen atom, it's directly bonded to the electronegative oxygen atom. There's less shielding, and therefore it would have the high chemical shift value. Whereas this hydrogen here, I said this hydrogen, all in the same environment, right? That would have a chemical shift value that's lower because it's not bonded to that electronegative oxygen atom. This is the one this is our triplet. It's because maybe it's bonded to a carbon that's next to. This hydrogen is adjacent to a carbon that's bonded to 2 hydrogen atoms. And the same for this side as well. But yeah, and because of that, that's why its chemical shift value is much lower. This is what's being represented here. Because it's not bonded to electronegative oxygen atom, so there's less of that. There's more shielding. So say there's more shielding or less de-shielding. But I say more shielding, we should say, because there's more shielding. It wouldn't have that same energy gap, and therefore the chemical shift is much less. And the same thing for propanol. So I'm not going to go through every single example here, but propanol. So methyl groups split into triplets due to the adjacent CH2 group. The middle CH2 group is split into a multiplet due to the adjacent CH2 group on one side and a CH3 on the other side. So this here, for propanol, right, is actually a quintet, but we call it a multiplet for some reason for AQA because they want to make it simple for you. The reason why this hydrogen here that is experiencing is bonded to, is adjacent to 2 carbons, right? It's adjacent to this carbon. Sorry, it's adjacent to this carbon here, and it's adjacent to this carbon here. The hydrogens bonded to this carbon here is 3. There's 3 hydrogens bonded to this carbon here, and there's 2 hydrogens bonded to this carbon here. We don't include this one because that's bonded to the oxygen, right? Really, this is a. Think of it like this, right? Remember, I draw the display form if you ever need help doing that, but you shouldn't need to over time. So overall, there's 1, 2, 3, 4, 5. So it's not a quintet, it's a sextet. This is a sextet. This multiplet that is talking about here is a sextet. But as I said, which means 6, it'll be 6, 2, 3, 4, 5, 6. That's how it will be represented on NMR. But obviously you can call it a multiplet. And then this here would be a triplet. This carbon here, I forget. This is hydrogen 1 NMR. This hydrogen 1 here is adjacent to a carbon that has 2. So therefore that'll be a triplet. 2 plus 1. Quick maths. Triplet. And then this CH, this CH2OH, that would have that would be a triplet as well. That would also be a triplet because it's next to these two hydrogens. So therefore, yeah, it's next to these two hydrogens. So it would be so 2 plus 1 again. So that'd be a triplet. Now you're thinking this. So there's no oxygen. There's no hydrogens here. That's why it's not triplet. So because there's one, 2. And it's not just for carbons. It's for any atom really. But yeah. So but there's no hydrogens bonded to this oxygen. There's sorry. I have to be very carefully. No, it should be for hydrogens. Yes, it should be for carbon. Sorry. Yeah. There's no hydrogens directly on this I have to be very careful with my wording here. This would be a triplet due to so this would be a triplet due to this adjacent carbon here being a CH2. So it's 1 and 2 here, and therefore that have 2 plus 1. That's a triplet. But this hydrogen here is a singlet. The reason why this hydrogen here is a singlet because the oxygen here has no hydrogens bonded to it. We're not looking at we're not looking here at the carbon because that's way too far away. We're looking at the oxygen here. The OH group is a singlet because it has no adjacent carbons to it. Because we're not looking at the this hydrogen isn't directly bonded to a carbon, and therefore it would be a singlet. There's no other hydrogens next to it, so it'd just be a singlet because n plus 0 plus 1 singlet. And that's what the exact is. So sextet, singlet, triplet. The reason why this triplet here, again, you can see here, why is this triplet so far away from the rest? Why? Because this triplet here is represented by this hydrogen here. Right? Because this hydrogen is obviously a triplet because of this these two hydrogens here, so CH2, so 2 plus 1, and that equals 3, and that's our triplet. But it's adjacent to the hydroxyl group, and hydroxyl groups are very electronegative, very electron withdrawing, and they would pull electron density towards the oxygen, making therefore is less shielding. You can go on from there on. The chemical shift will be much higher, and hence the chemical shift is much larger. And that's it for this part of the video. I'll do part 2 later, but that is it. I'm going to watch Man United versus Crystal Palace. Hopefully we win. Don't troll me if we lose. Hopefully the video is helpful, and that is it. Thank you for watching.